benefit described yesterday, in the sense that yesterday was maybe a bit vague or maybe a bit unclear. So now what do we actually do with this? And so today I can hopefully start to convince you a little bit that this kind of categorical formalism is actually useful. And so that amounts to kind of starting to formulate a couple of ideas that underlie probability theory in this language. And Paulo had already started doing that yesterday by introducing the definition of deterministic morphisms. And that's where I want to continue now. So let me just write down the definition again. So from now on, everything that I'm doing is taking place in a Markov category C. And then we can also talk about what these things mean in our examples, and maybe with particular emphasis on the commutative C-style Schmer case. Okay, so a morphism of X to Y, we call it deterministic. If it commutes with copying, essentially, right? Or as Paulo said, when you read it in the Heisenberg picture from top to bottom, if and only if it's a homomorphism with respect to the copy. Okay, so in a C-star example, C-star case, Paulo already mentioned as well, these are the star homomorphisms. And maybe we can just recall why that is the case. So remember that the copy is the multiplication. And so then this is literally just saying that F must preserve the multiplication. And well, we're already assuming that F is positive, a positive map. In the commutative case, I mean, we'll just stop saying completely positive since it's equivalent to just positive. And well, as a positive map, of course, it's also self-adjoint or preserves the involution. So we have the star homomorphism. And well, it's unital anyway because of the condition that in the definition of Markov category, the final condition that the scarred morphisms are preserved anyways. Okay, so this is what deterministic means. Now we can actually prove, we can do some simple proofs about this concept and prove a number of simple consequences. So for example, so this would be a kind of first lemma now, that deterministic morphisms are in particular closed under composition. So if I have an F and a G and I can compose them, then also the GF is deterministic. And the proof is just a simple string diagram manipulation. I imagine I have another G on top of this. Well, then I can first pull the G through the copy and then the F, and then I get both the G and the F on top. Okay, but in fact, more is true. They're also closed under the parallel composition or the tensor product, and they're similarly simple diagrammatic proof of this. And so we can in fact say that the deterministic morphisms form a what's called Cartesian monoidal subcategory. Okay, so well, first of all, I don't want to be very precise about what the Cartesian means. But if you're familiar with the universal property of products in a category, and this just means that a monoidal structure, the tensor, on this subcategory is the categorical product. And so in particular, this means that if we look at a deterministic morphism whose codomain is a tensor product, so x times y, then we can decompose it uniquely into its components, or it's uniquely determined by the corresponding projections to x or marginals to x and to y. And so let me also just kind of write this down, what this looks like grammatically. If we have the deterministic morphism like this, then we can now write it as so basically the conditional product of its marginals, and the equation that the diagram that I'm now about to draw should remind you also of conditional independence I had introduced yesterday. Right, so then if we have the deterministic f like this, then this equation holds, and it's not so difficult to see that this is indeed true from the definition of determinism, because by assumption if f is deterministic, we can pull these two through the copy and put them down here. So then what we get is just, well, I guess I can actually draw this on top here. We pull this through the copy. We get the copy of x tensor y up here, which factors in the way that I've just drawn now already by the definition of CD category at this multiplicativity condition on the copy, and now discard the two middle wires. Okay, but now we can simplify this thing up here by just using the co-unitality. And so then we just get the identity on here. So this just disappears. And this is how you prove it. Okay, yeah, but in maybe for commutative C-star algebras, does anyone can anyone formulate this equation there or say what it means in that context? Okay, well,
Homomorphism? That's an homomorphism?
Yeah, so here we're assuming that f is a homomorphism, and so we have C-star, commutative C-star algebras A, X, and Y. We're assuming that we have a homomorphism from X tensor Y to A. So in this case, then I'll write it down. But what it's saying is that now, let's say we plug in elements X and Y here, and now we're looking at f of X tensor Y, right? On the left-hand side. And what we have on the right-hand side is just X, and now here the unit. So this is f of X tensor tensor 1 for this part. And now times the thing on the right, f of likewise 1 tensor Y.
Independence. It's independence conditional.
Yeah, exactly. So this is conditional independence, and that may also be apparent from the diagram, since this diagram is exactly how I introduced conditional independence yesterday. And maybe most of you are most familiar with it in this form. familiar with this property in this part. Okay. And yeah, so we denote the subcategory by C subscript det for deterministic. Okay. Should I also maybe make a little more explicit what this equation means in measure theory probabilities in the case of Borel stock? Do people want to see this?
Yes, please.
Yeah, okay. All right, so in Borel stock, so now here we have Markov kernels as our morphisms. Oh, and maybe I should introduce, yeah, no, X, Y, label these wires just to be clear about what sort of the typing is. And so in Borel stock, the way that you can approach such an equation with multiple outputs is just by seeing what happens when you choose a measurable subset for each output. And then you kind of plug those in. And it's enough to check the equation on these, basically, because then you got rectangles that generate a sigma algebra, and that's enough then to kind of by standard measure theory results to check the thing on this, basically just like how it's enough in this case to check an equation on elementary tensors because these span the whole thing. Okay, so this means I'm going to plug in measurable sets for all measurable S. So elements of the sigma algebra on Y. No, sorry, they're both on Y, right? ST are elements of the sigma algebra on Y, and then also for all little x as input. Okay, sorry, now I'm thought of it already. Okay, so let's see what we got here. So here, or maybe let's start at the right-hand side. The right-hand side is maybe a little easier. On the right-hand side, we would get f of s given x, right? With our measurable set s for here, and we're looking at what's the probability to land in the set s with this output given the input little x, and likewise for this one. So this would be f of t given x. Now, what about the left-hand side? Well, under what conditions do we get an output that is in S here, and an output that is in T here? Well, that's precisely if the output of F is in S intersect T. Right? If it's in both S and T. So here we have S intersection T given X. Yeah, and so this is the sort of when you apply the machinery of how to translate string diagram equations into the measure theory and Borel stock, this is what you get a priori, and this is maybe not completely. It's not completely obvious what this means yet, and so we should maybe look a little bit more at what this is. We should try to simplify this a little more, right? So in particular, if we take S and T to be equal, then we can see something interesting. Then we got S f of S given X should be equal to f of s given x squared, right? So this is a consequence. But in fact, it goes both ways. So this is an equivalent formulation of the condition. And the converse is also not so hard to see. I mean, this is not saying that our probability should all just lie in 0 or 1, should all be 0 or 1. And if you already know this, well, then you can kind of relatively easily go back and prove that this equation holds for all s and t. Okay, so under what conditions, what does it mean to have a Markov kernel that has just probabilities 0 and 1, where all the probabilities are 0 or 1?
It's just concentrated on some.
Yeah, exactly. So we have to be a little careful, but this is not true. This is one of the ways in which general measurable spaces are not nice, and it's not something that we want to work with. Because this is not true on general measurable spaces. That when you have just a 0, 1 valued, a measure taking only the values 0 and 1, that it's necessarily a delta. But for standard Borel spaces, it's true, and it's a delta at a unique point. So both the existence and the uniqueness in this case is important for us. So we can say, or equivalently, this is actually not so easy to prove, and so hopefully you don't, nobody's going to ask how do you see this. But this is true in under our assumption that we're in standard Borel spaces. Okay, so f of equals, so now let me write it like this, delta g of x, right? But for fixed x, the probability measure that we get is a delta at some point g of x. And essentially because of the measurability assumption that we make that a kernel is supposed to be measurable in x, this g is now an actual measurable function. Or and yeah, as I said, also unique, measurable function. And so now I want to emphasize this to distinguish it from Markov kernel, since I kind of generally use the same notation, but now it's an actual measurable function. Okay, and so then when we talk about deterministic morphisms, especially in the context of Borel stock, we are a little sloppy, and then by identifying the deterministic Markov kernel with the corresponding measurable function, it's just kind of a bit of an abuse of terminology or notation if you want. So if you allow me to do this, then we get that Borel stock that, so the subcategory of deterministic morphisms, deterministic Markov kernels, is just the category of standard Borel spaces and measurable functions. And so this is pretty similar to how in this case we have recovered the star subcategory of star homomorphisms. Okay, what do you think we're gonna get for if you remember our kind of other example of thin-set multi, where the morphisms were this, well, multi-valued functions, or kind of just possibility-valued stochastic matrices. What is the deterministic subcategory of this going to be?
The matrices which are only 0 or 1?
Yep. Well, you mean any number of zeros, any number of ones, or?
No, they have to satisfy the completion. Like doubly stochastic or unistochastic with one of the two.
Well, not in the usual sense, because I mean we don't have. Now the entries are just Boolean 0, 1, so kind of like possible, impossible, true or false, right?
Ah, sorry, this is okay.
Multivalued function y with the sum which is 1.
Yeah. So the morphisms are multi-valued functions, meaning that for every input value, you get at least one possible output. That was the normalization condition. Yeah.
So then you would just get normal functions, no?
Yeah, exactly. We just get, and this again, this may be intuitive if you look at the diagram. So on the left, we're guaranteed to get the same output on these two branches here. Whereas here, if f can have several possible outputs, well, in that case, you can get outcome pairs that are not equal here as possible. And so that's how this equation then enforces the single valuedness. And yeah, so thin-set multi, deterministic subcategory, that's if we make the same abuse of notation, literally equal to thin-set category finite sets, and just maps functions. Okay, so
Normalization
yeah.
doesn't play a role in this sense to get functions.
What does?
The normalization, having normalize all the possibilities doesn't play a role for the.
It does insofar as if we didn't have that, then we would get partial functions. Then it could, it could still be like you get no output for a given input, and then the equation would still hold because then kind of both sides fail. So you would, in order to get actual functions, then you still have to impose the totality or the normalization separately, and we kind of do this as well. And or yeah, if you work with these CD categories, then this is something that one needs to take care of and keep track of. Okay, any more questions about this? All right, yeah, then I'm going to move on to the next topic, which would be that what we have so far is kind of a pretty bare bones definition of Markov category. It's maybe a bit like the definition of a ring or something, right? There isn't really anything on top of it. And now if you want to develop some theory of this and prove some theorems, but there's very few theorems, and especially very few interesting theorems that hold for all rings. And so likewise, I guess one cannot expect to get any sort of interesting theorems that hold for all Markov categories. But we want to impose some additional conditions or some additional axioms in order to kind of narrow it down to a certain class of Markov categories, which, well, in particular capture those that are of interest to us. And so there's a class of these axioms that we have. that we call information flow axioms. And I hope it's going to become clear why we call them like this. Oh, and maybe I forgot to say concerning the analogy with ring theory, I think it's kind of accurate in the sense that why do we do, or why have people maybe started studying rings in general? And well, okay, I'm not sure how historically accurate this actually is, but I imagine it's mainly because rings are kind of generalized number systems, right? People had a bunch of number systems, integers, rationals, reals, and so on. Maybe natural numbers are not a ring, but close to. And so then at some point, well, you just arrive at a general definition. And then work with that and then try to prove theorems about this concept. And maybe find other uses for it as well, which obviously has been very successful in algebraic geometry and so on. And I think that the same thing applies to Markov categories as well. We have several kind of theories of uncertainty, right? We have measured theoretic probability. We have more like this non-possibilistic non-determinism. There's variants of imprecise probability, other kinds of possibility theory. There's quantum probability, which, as we've already kind of talked about a little, doesn't exactly fit into this framework, but needs something a little more general. But roughly, yeah, Markov categories are the general definition of the theory of uncertainty. And now we can try to develop general theorems about this, just like ring theory develops general theorems about number systems. Okay, yeah, but for this we want some additional axioms. And one of the kind of, I think maybe nicest ones is what we call the positivity axiom. And it's called positivity precisely because it's related to the non-negativity of probabilities, and also in some way to the positivity, more like in a complete positivity sense. So our Markov category C, we call it positive. If whenever you have composable morphisms F and G, which are such that the composition G composed F is deterministic. Yeah. Then another equation follows, and this equation is looks like this. And if you have this kind of situation, then you can pull the F through the copy, even if the F, we're not assuming the F to be deterministic. Only the composite is deterministic. So positivity means that this implication holds. And I want to claim that this equation is actually very intuitive, and or explain the intuition behind it if you think in terms of computation and circuit diagrams. Because then what we have is that we have a computation which has kind of two parts, two phases, and the whole computation gives you a deterministic result. There's no uncertainty in it. You can compute it from the input in a definite way. Okay, well, but on the other hand, what we're doing here is that on the left we got the result of the computation, And on the right, what we look at is sort of copying the value of an intermediate result and outputting that. So here we're looking at not just the result of the computation, but also at the intermediate result. But no, because the whole computation is deterministic, well, you might as well do that independently. You might as well compute the actual result independently of the intermediate result. And this is what the right-hand side does. So that's why when one can think about this equation, maybe why one might expect it to hold.
So you're not saying that the intermediate results are going to be equal on the nose. You're just saying that the uncertainty in the intermediate result is independent on whether or not you copy it before or after doing. Is that?
I'm not actually sure what equal and nose would
I'm saying
mean.
that if you wrote down this, you're not saying that the intermediate result that you get on the left.
So
There's no equality here because they're not actual functions, right? But if you think of it in terms of processes, you're not saying that the intermediate result is going to be equal 100% of the time on the left and on the right. You're just saying that
there's no statement about doing these two things in parallel or simultaneously. We cannot talk about how they're correlated or not. We're not talking about that, right? We're only talking about what happens when we do this, and maybe this helps what the distribution is.
right. The distribution of both, if you think of it in terms of random variables, and the distribution on the left and on the right of the intermediate results are going to be the same.
Yeah. But there is no joint distribution here. And maybe so if you're used to thinking in terms of random variables, and all random variables have a joint distribution, I think that is a way of thinking that is, well, even for real world modeling, often not adequate, right? And so maybe it's good to try and kind of prevent that way of thinking anyways. Yeah, there was some.
Oh, so it's like if f is like take a random number and multiply it by 2, and g checks if it is even. Like you always get that it is even, but then you have some random kind of thing.
Mm-hmm. Yes, also that's maybe a little too trivial to be a good example, because then the GF is even actually constant, right? Not just deterministic, but even constant.
Yeah, that's true. Can G be non-deterministic too? Indeed. Or does this force G to be deterministic?
I mean, the implication holds only if it's deterministic, and in general, the equation will not be true otherwise. Let's say in Finstock, it will, or already also in FinSet multi, if this does not hold, then this will also fail typically. Then maybe what Arnaud was saying is, yeah, maybe also relevant, or maybe by thinking of it in those terms, maybe then you can. I don't have a good example offhand right now. Okay. So now all of our examples of Markov categories. So by these, I mean our examples that we've learned about so far are positive. And yeah, so to prove this with Stock, for example, you can do kind of this kind of procedure. And it's not completely trivial or not obvious to prove, and you kind of need to, but it's also not hard. I mean, you just need to use the non-negativity of probabilities. Okay, yeah, well, so now, maybe unsurprisingly, since it's an additional axioms, there are also examples that are not positive. And so these are maybe displayed as the counterintuitive behavior, because I mean, I had kind of argued this should hold based on our intuition about computation. And so this is then maybe one way to make precise that these counterexamples are bad theories of uncertainty because they don't conform with our intuition. And one such example is if we take, for example, Finstock, and we modify the definition to allow negative probabilities. And we call this we still get a Markov category, since just in the verification that we get a Markov category, we never needed the non-negativity of probability. And so this is the Markov category that we call Finstock plus minus, just to indicate here that negative probabilities are allowed.
Basically, it's measured here. Finite measure.
Yes, we're normalized. I mean, we still have the normalization, but otherwise finite measures, yeah. Okay, yeah, I mean, then in this case, one can write down very explicit examples with numerical values for the matrices that violate this. And this is one thing that's wrong with negative probabilities in the way that where we can kind of very clearly see how they are in conflict with our intuition. Okay, so this is a kind of a typical pattern for how what our information flow axioms look like. Typically, there's an assumption of one or two equations, and then another equation is concluded from that. And I think I'm not gonna go into any other ones. We have a bunch of similar ones like this that again hold in various cases and don't hold in others. But this is kind of roughly what this looks like. And then one can use in proofs of theorems about probability and statistics. Okay, there's one more axiom that we really use quite a lot, and that I think is also conceptually very important, and I suspect that most of you will agree with this, namely conditioning. I want to have a concept of conditional probabilities, and well, in Finstock that's not so difficult to define concretely, right? By dividing as usual. And measured varied probability is already a lot more subtle, but in the context of Markov categories, it turns out that if you just take the usual definition of Finstock, you write it down in categorical terms, and then you interpret the result in Borel-Stock, it turns out to be something nice in measure theory. And so now I'll write down what that definition of conditioning is. So say that C has conditionals. If for whenever we have a morphism that has two outputs, and of course it can have any number of outputs as long as we're sort of partitioning them into two subsets. It should be possible to factor this thing into kind of first producing an x, first producing the output that corresponds to x, and then using that value together with the original input value to kind of produce the second output. And then this second process that produces the y, that's what we call the conditional. So if there is a morphism f given x, so this is a capital X corresponding to the object, denoting the object here, that takes, yeah, as I said, two inputs, X and A and output something of type Y, such that the original F factors. And now I'm just kind of drawing what I already said. We first do the original F, but we only keep track of the X, so we discard the Y output. And so this is the marginal that only produces the X. And now we take this conditional separately. I guess my drawing is not very good, sorry. Have a little more space. And we input the original A and the X into the conditional, and that produces the Y output.
We ask for uniqueness, or do we
No,
get
that's kind of a bit of an annoying issue that we have to deal with, and somehow people have tried to make it more unique or somehow. But as far as I'm aware, there isn't really any satisfactory solution to it, unless maybe Paulo has a satisfying answer to uniqueness problem with conditionals. No.
See, there's the opposite, right?
The opposite?
Yeah, you proved that if conditionals are not unique.
Yeah. Right. If in a Markov category where conditionals are unique, it's something like every morphism is deterministic or somehow it's completely degenerate. I forgot the exact statement.
But okay, almost sure it's
Yeah. So they are unique up to almost sure equality, which we can, that's basically I'm going to get to almost sure equality, and if you know that definition, it's kind of relatively easy to read that off directly to diagram. Okay, but so conceptually the idea is that this factors F into two stages, right? Once the first stage, which just generates an X output, and the second stage, which generates an Y output. Then by applying this repeatedly, of course, we can do the same thing. If we have any number of outputs, we can then factor it into stages. And I think this is what conditioning, to my mind, at least really is about, to kind of be able to given A, little a on the left-hand side, right, for arbitrary values, input and output values. So this is on the left, and then on the right, we get first of all the marginal. So maybe I'm gonna kind of spell this out and write it explicitly for sum over Y prime. So yeah, that's this thing, right? And then here for the conditional, we just got conditional Y given X comma A. Okay, and now, well, assuming that this thing is non-zero, we can divide by it, right? And then we just get, so then in this case, we do have the uniqueness. Meaning that I can take it to the other side. And then here I get basically Bayes' theorem on the left-hand side, right? It's a little more general because we have everything depending on this. Everything can depend on this extra parameter A. But for Finstock, I mean, that makes no difference. Just have an extra index. And for Rellstock, that creates additional subtleties because now we need to keep track of the measurability in A as well. That's a bit makes things then really a bit more tricky. Okay, yeah, now we can also instantiate this in Rellstock. And it turns out that conditionals still exist in that case. And in that context, these are known. I mean, it's a well-known concept. One of the standard concepts of conditioning in measure theoretic probability, namely the concept of regular conditional probabilities. Yeah, with an additional measurable parameter A potentially. Okay, so well, maybe some of you would wonder now, well, what about conditional expectations? You know, and Paolo already, since this is maybe what you're most familiar with in conditioning in that form, Paolo already mentions a little bit about that. And these kind of arise, in a sense, you can reduce one to the other. And they're kind of equivalent concepts. And I think I'm happy to talk more about this during the coffee break or something, but maybe rather unless there's really strong interest in seeing more about how conditional expectations fit in, I would move on to the Finetti theorem.
If you can give just an intuition about.
Yeah, maybe okay. I can say it for Bayesian inversion then maybe. Okay, let me then sketch it in a kind of C-star case setting already. So then let's consider a special case, or let's consider a case where this F has a certain special form. Namely where, say, we have a state phi on some C-star algebra or something A. And then we also have a sub-algebra, C-star sub-algebra or whatever. E, and well, the inclusion itself is a non-trivial morphism, right? In this sort of language, I need to write the inclusion also as a box because it's an actual map. So let's maybe just write this as I for inclusion. I mean, it's deterministic, but that's not so relevant here. Yeah, and now what the existence of conditionals. Oh, maybe I should add the caveat that for commutative C-star algebras in this category, conditionals do not exist in general, which I guess is probably obvious to you, to many of you, because, well, in a C-star context, you don't have the relevant completeness to get conditional expectations. But disregarding the existence for the moment, if there is one, then it's going to amount to doing this factorization in two stages and sort of rebalancing this diagram. And so to say that I first want to actually produce the B output. So that means I'm going to consider the restriction of the state to B. And then to get to A, no, wait, A, B inclusion. Oh, yeah. Then we have our conditional expectation here. Right, so this corresponds to this conditional. There is no A, we don't have any A, so it only has one input, or the A is trivial, so it just has basically this one input, and that's exactly from the X, which now corresponds to our B. And here we have the marginal of F, that's exactly this, the restriction applied to B. Okay, and now, well, maybe it's worth writing down what this equation now says, again, in terms of evaluating elementary tensors. Well, then we get for, let's just say, little a and A, and little b and B, that here I don't have to write the inclusion as a map, right? I'm just going to consider B as a subset of A. So phi of AB is equal to phi of, no, sorry, BA. Let's just be maybe consistent with the order of elements up here. B virtual expectation of A. Okay, does this make sense? It's a little, I don't know. I'm a little rusty on these things, but is this sensible?
Should be the other state restricted.
Oh, right. I thought there was something wrong.
Yeah, well, but since you are not writing I, it's
Yes.
like implicit.
Okay.
Because the right hand side should be the I star of phi.
Yeah.
But it's clear the equation.
Okay. All right. Then yeah, just assuming it's kind of correct, I'll just leave it. Yeah, leave it like this. Yeah. And of course, in non-commutative case, we may have kind of things coming multiplied from both sides here, so on. But since we're in a commutative setting, it should just be this. Okay, so this is kind of maybe the most important axiom that we generally work with. And there's a couple of things that one can do with the existence of conditionals only. For example, we've proven, or basically we've developed a theory of Bayesian networks with Markov properties, so a character called deseparation criterion, how to recognize causal structures in terms of conditional independences for all Markov categories with conditionals. Okay, there's now one more concept, one more definition. No, actually, there's a couple more kind of definitions I need to introduce before we can get to the definite theory. But yeah, we've already briefly talked about almost sure equality, so I should just introduce the relevant definition here. Now again, we're in a general Markov category. You can say F and G are E almost surely equal. Or given some P from A to X. If you want, you can take this A to be trivial, and then the P is just a state or a probability measure. The F and G maybe could be deterministic, so they could just be functions, measurable functions, but they don't need to be. This can still be, this still makes perfect sense in general, and they're not deterministic. So yeah, if, now we need to write down the actual definition, if, and this is just, if, some equation within diagrams holds, namely if I can just replace F by G in all kind of situations like this that are preceded by P. So yeah, almost for equality, in other words, is just a shorthand notation for equations like this. And it's a convenient shorthand, and a shorthand that comes up quite a lot. And that's why we introduce a separate notation for it, namely F equals now subscript PAS. And again, keep in mind that we don't have any probability space here where all our random variables would live for anything. I mean, we don't even have random variables. We have Markov kernels, and there's nothing like a joint distribution. Okay, but maybe also because of this, it's probably worth kind of spelling out what this amounts to in Burrell-Stock, what this equation means in measure of theoretic probability. And yeah, well, what it means is that F and G, or maybe let's talk about, actually, sorry, let's look at the intuition behind this equation first. What this does is that for any output X that can actually occur from P, their F and G behave the same way. Well, what we're looking at is, by looking at X and Y as overall outputs, we're looking at the joint distribution of input and output to F, and the joint distribution of input and output to G. And the equation says that when X is distributed according to P, then these joint distributions are equal. And while the P it doesn't need to be just a single measure, it can depend on an additional parameter as well, in which case this equality should hold for all values of this parameter. So that's what this is saying.
Sorry, you could hear this. So if you discarded X, then you would get that P composed with F is equal to composed,
That's
which is
exactly
like a weaker version of.
That's exactly, yeah. Mm-hmm. That's kind of saying just the push forward of P is the same, but it does not mean that F and G are almost really equal. But it's clearly a necessary condition, yeah. Mm-hmm. Okay, so now let me write down what this formally amounts to in Burrell-Stock. And so there, the formal formal version is this: if we look at the set of all X, where F and G are the same, are literally the same probability measure on Y, then this set should have measure 1. And it should have this for all values of the parameter A. this is again kind of special to Borel-Sorg and is not generalized to all measurable spaces, unfortunately. And in general, it's not even clear if this set is measurable. And I guess it's not in general. But in Borel-Sorg, it takes this nice simple form. Okay, and if we now go back to the definition of conditionals, at least maybe it's at least intuitive that if you now imagine you have another conditional, you have another f given x that satisfies the same equation, well, then this diagram is the original one, and if the new one, these are equal, and it kind of, if you just look at it, I think it should become clear it is of a very similar form as the almost row equality, and so then you can actually conclude a conditional is unique up to almost row equality, and this is purely formal now.
Equality where P is F, right? F, almost equality.
Almost row equality with respect to not exactly F. I mean, it's a sort of modified version of the marginal of F, since you also need to keep track of, also have this additional thing down here. But pretty much, yeah. Okay, yeah, so I actually need two more concepts. But I hope, yeah, I hope it's interesting since they're all kind of, I think, fundamental concepts of probability. And the next one is, I think, also going to have an interesting interpretation, and again, in the operator algebra context. So yesterday, if you recall, I said something along the lines of a Markov kernel. Well, I had kind of written down the definition as this kind of map taking these two arguments, one just the input value, and then the other one a measurable set. And had said something along the lines of, well, this is just a map taking values and probability measures. And there's now at a categorical level, at a general framework, abstract framework, a way to make this correspondence precise to say that a morphism is the same thing as a deterministic morphism. So it's a probability space valued, probability measure valued map that's a deterministic morphism in our setting. But taking values somewhere else and in a space of probability measures. And this correspondence is something that we can make precise, like that I can formulate for Markov categories in general, and that we also use quite frequently. So in Borel-Sorg, yeah, let me just write this down. We have a Markov kernel. X to Y. Now I'm gonna, like Ors, use these horizontal lines to denote something like canonical bijections, natural bijections, adjunctions, things of the sort. Correspondence between Markov kernels, like this, and measurable maps. From X into then what we denote by Py, the space of probability measures. on Y. And well, this space has, well, it's not, I mean, maybe you usually would consider it as a set, but this itself has a canonical sigma algebra. Maybe I'll spare you the definition now, but this turns out to be then a standard Borel space again, if Y is one. And we can define this in such a way that the correspondence matches exactly, or the measurability of this map matches exactly the measurability I had in the definition of Markov kernel. And if you recall the details here, then maybe it will be clear what the sigma algebra here should be. Okay, and so when we have a Markov kernel like this, we can look at its counterpart as a measurable map, and just to distinguish them notationally, we denote this by F sharp. Yeah, it's this kind of musical notation of sharp and flat is somehow kind of used frequently for adjunctions and this kind of canonical counterparts of morphisms among such correspondences. Okay, yeah, and this is clearly bijective. So yeah, maybe just as a quick note or exercise question, what is a counterpart of the identity on some, let's say, on some standard Borel space X? What do you think the sharp of its identity is going to be? Yeah, exactly. Yeah, right. So the identity Markov kernel, and I guess I actually forgot to say this yesterday, is the one that just associates to every point little x the delta at x. And so this counterpart is just the measurable map x to px that maps every point little x to the delta at x. So yeah, this is something that we get when we start with the identity up here. Now suppose that we start with the identity down here. So suppose we take our x, I mean this is bijection, it's supposed to be bijective for all x and y. So in particular we can take x to be py, and we can take the identity here. So now consider that as a measurable map. What do you think is the corresponding Markov kernel going to be?
Is it some sort of expectation?
That's one way to put it, yeah.
Because you would want something that goes from measures on y to values on y.
It goes to, well, from measures on y to y, if you look at the literal typing.
Yeah, but it's a Markov kernel from.
Yeah. And so it's maybe more a question is maybe more like how to think of it. And the way that we think of this is sampling. So this is the Markov kernel from py to y. And I'll just write it down what it does as a Markov kernel. This is the counterpart, the unique Markov kernel with counterpart is the identity. Okay, so now what does it do concretely? If we take some element little y, no, sorry, the element, the input is a measure on y, right? A probability measure. So let's call it, shouldn't call it y, but let's call it mu. And now the output, well, should be a probability measure on y, and of course it's going to be mu itself. So, meaning that if I evaluate this on some measurable set S, I'm going to get mu of S. This is the canonical thing to do, and therefore it kind of obviously must correspond to the identity under our bijection. Well, the reason that we think of it as sampling is because that kind of operationally is what it does. It takes a probability measure, and so if you think of a Markov kernel as a random process, as something that produces an uncertain output, but it produces an output, an actual value, it's just a random one, then this thing is exactly sampling, right? You take a probability measure, you get a thing of it, this thing is getting an actual value for y, a random value. That's what sampling does. Okay, so this is something that is a structure, additional structure we have in the REL stock, and maybe from this description, it's maybe already kind of apparent that this is just something that can be formulated at a general categorical level, since this is just kind of conceptual structure. And so now I can write down the definition. C is what we call representable. If for every y, every object y, there is what we call a distribution object py. So this terminology is also introduced here in this definition, which is such that there is a bijection between general morphisms landing between morphisms into y, arbitrary ones responding to Markov kernels in the case of Kowalski, and deterministic morphisms into an distribution object. And well, of course, this, as is the case in category theory generally, these should be suitably compatible as we vary x in the sense of the natural transformation. So natural in x.
Only in X? Or do you also regard some kind of naturality in Y?
That's automatic. So I don't need to postulate it, but you can then conclude that the naturality holds, and this P distribution object construction is functorial to start with.
So that's a very clear observation. Again, isn't this telling you that you can get to, I don't have the correct adjective, let's say higher level of abstraction where your Markov category and your randomness is actually only deterministic, and what you're seeing in your Markov category is just the projection of some very ordered and deterministic way.
Yeah, that's a good way to think about it, and it's sort of actually, I haven't explained where this word comes from, but in a sense, that's where this comes from. So if you do this, what you're describing is kind of a general principle for how to construct Markov categories. So you start with a category of deterministic morphisms.
Yeah.
You have an additional functor on it that corresponds to the P, and this functor has an additional structure making it into what's called a monad. and then you take the Heisler category of this monad. So you basically replace morphisms from X to, instead of taking morphisms from X to Y to be the original ones, you define a new morphism to be an old morphism from X to PY.
So what would be this category where everything is deterministic in the case of Borel stock?
Just the Borel nest, so the measurable spaces and measurable functions. And so you can, you can construct Borel stock like this, and this applies in many other cases. Applies to Vincent multi as well.
Is there an advantage to work with the Markov category and not with the Cartesian closed deterministic category?
By Cartesian, do you?
I mean, perhaps I didn't understand that. As far as I understood, there is a category which is fully deterministic in the sense that all the morphisms you are considering, so it's a Cartesian closed category, right?
Not Cartesian. You mean? I think you just mean Cartesian. Cartesian closed, and then you have exponential objects.
No. Then Cartesian. What you said before about deterministic.
Yeah.
Is there an advantage to not working with?
Yes. In a sense, this is a Markov category. So all about exploiting that advantage of having the string diagram calculus, have been able to talk about conditionals, for example. This is really messy to formulate directly in terms like that. Yeah. I mean, I haven't actually tried, but I think Paulo has.
Yeah, also the thing is, you don't just work in the Cartesian category. You have to modify the composition a little bit, because you see, you want to compose X to Y and from Y to Z. Now you have to you have PY there.
Yeah.
So it's a whole thing that makes things a lot more complicated.
The Markov category is just a lot easier to work with.
Yeah, from my perspective, it's not, because from my perspective, from if you look at the quantum, let's say a quantum version of this, when you lose the outcome space, you lose everything that you have in the Markov case.
I'll try to convince you.
Yeah.
But
it's not that I'm not convinced, is that I in the quantum case, I see that I cannot get something like Borel stock. So perhaps in that case you are forced to use the.
No, but in Borel stock, the quantum version. Yeah, let's do the quantum version of this.
But I didn't. Sorry. I don't want to.
I wanted to explain this anyway.
Okay.
Since given this audience, at least so for commutative C-star algebras with this amounts to.
Yeah, but for commutative C-star algebras, they are too nice in some respect.
We can. I'll talk about non-commutative case on Thursday then.
Yeah, but please don't be deranged by my observation. Just
no. I mean, I have this in mind already. Anyways, yeah, and I'm happy to.
And sorry if you don't mind, this is not the statement that the deterministic subcategory is reflected, right? Because you have the adjunction going the other way.
It depends a little bit on what you call reflective. So I think usually reflective requires the condition that your subcategory is a full subcategory. So whenever you have two objects in it, it also contains all morphisms between them.
Which is not the case.
And that's really not the case here. It's more like an opposite thing, that it contains all morphisms rather than all objects. Contains all objects, but not all morphisms between them rather than the other way around.
Okay.
So this is maybe a little unusual from that perspective, yeah. Okay, so now let's consider the case of commutative sigma C star. Sorry, not sigma I. Yeah. Been working on these sigma C star algebras recently. It's candidates for this quantum measurable spaces. That was just a slip. So commutative C-star algebras are with CPU morphisms. That was our category, right? Yeah. And this is the analog of, the analog of Borel stock now, right? And so let's see if we can get a correspondence like this in this setting. And now maybe to make it most clear, I'll when I write down the arrows now, I will already reverse the direction of the arrows, right? So now the distribution objects are going to be on the left. so that we have arrows as actual directions of maps in our Heisenberg picture. Okay, so we want the correspondence between, well, just positive unital maps from this maybe psi from A to B. And what do you think we're going to need for what should its homomorphism counterpart be? We need some new C-star algebra associated to A.
The double dual. Just because it's the only thing that I.
Well, but A could be finite dimensional, in which case it's its own double dual, but you would not get this, right? I mean, maybe it's not possible. Or just think about maybe A as a vector space, right? Forget about the positivity. Then you just have a linear map out of A. What algebra can we associate it to A that will make it multiplicative?
Matrices on like linear maps from A to A, but that's.
No. So the answer is the tensor algebra, which means we just take basically the Fock space, right? The tensor powers of A, direct sum over all of them. That has the canonical multiplication just on a formal tensoring, right? This is then called a tensor algebra of A. And well, it's still not a C-star algebra yet, but just an algebra. But I mean, we can't do everything just for algebras. Forget about the norm and completeness. Then it literally is just a tensor algebra. Maybe need to be a little careful with the identity, but need to almost a tensor algebra modulo quotient and identifying the zeroth tensor power with the unit of the algebra. And for C-star algebras, commutative C-star algebras, so then we need to take that completion. And this turns out to be something quite nice. I can't quite reproduce the proof right now, since basically this was mainly done by a postdoc Antonio. But so he has shown that this is basically the algebra of continuous functions on the state space of A. Where, of course, the state space has, as usual, in the weak star topology. And this is a universal property of the state space, which, as far as I know, has not been known before or not formulated before. And we also have a non-commutative version like this that I can talk about on Thursday. Okay, so yeah. What we could do now here to do the analogous thing of starting with the Cartesian category, then using this functor on top of it, what that would require us to do is to start with the category of commutative C-star algebras, and a non-commutative situation in this context is pretty similar. We'd start with commutative C-star algebras and star homomorphisms. Consider this functor that forms commutative functions on a state space, and when you propose morphisms, you have to kind of iterate the application of this functor just in order to get to positive unital maps, or to get to this description. I mean, you rather would. I assume you would rather work with positive maps directly in this form, right? This is nice, but and this can be useful to work with, but I mean, I don't think you would want to construct your category of commutative C-star algebras and CPU maps by starting here and using this, right? You just define it into as morphisms positive unitary maps to start with. You basically construct a Markov category directly.
I don't know, beauty is in the eye of the beholders.
Yeah, okay. Yeah, maybe, yeah. I mean, okay. If you,
That's
that's
a very
fine.
nice construction, so thanks
Yeah.
for sharing. It's
Mhm.
really, really interesting.
Okay, yeah, I mean, you can construct it either way, and to me at least, a simple, straightforward construction is then easier to work with, but okay, you can either, in the end, it turns out to be equivalent.
The good news is that you can choose.
Yeah. Okay, then this is probably, oh yeah, maybe, okay, just to finish this off, I suppose we can still also write down what a sampling morphism is in this case. So now we have to reverse arrows. So this has to be a canonical positive unital map from A to continuous functions on a state space.
Expectation bound.
Yeah, and there's an obvious thing of what one gets, and of course that's correct. So we take an algebra element little a, and we map it to, well, the continuous function on a state space that just evaluates states on A. So the evaluation map, which of course is continuous by definition of the topology in a state space. Yeah, and so this is basically sampling in the Heisenberg picture.
But it's not quite sampling, because sampling is taking out an outcome in the outcome space. Here it's just taking an expectation value of an observable, so it's not quite the same.
I can't
Like in
quite
this algebraic
answer that
picture.
right now, but it must be, I mean, there must be some way to make this intuition apply.
I guess
'cause-
when when the little a is something like the indicator function of some measurable set, or some set, okay? Then we're like kind of seeing what's the probability of actually observing that.
Yeah, but again, this means that you are identifying that the algebra A as the algebra of functions on some outcome space, which as soon as your algebra A is non-commutative, you cannot do that.
This is all commutative algebra.
This
Yes,
is in a
it is a
commutative
commutative.
context, and maybe hold off with the non-commutative
Yeah,
stuff
that's
until
sorry.
Thursday.
Just I always go there. So
Yeah.
I will shut up.
Okay, but this should have the completely analogous interpretation to this in the Heisenberg picture. Although, yeah, right now I also don't really see it. Okay, then yeah, I suppose that's a good time to stop for today. So yeah, thanks.